Hi, my name is Oliver Barry. I'm a finance major at NYU Shanghai.
Hi, my name is Haibo Li. I'm a math major at NYU Shanghai.
And this is our final project for Intro to Machine Learning on General Text Summarization.
In the following video, we're going to talk about the introduction of our project and the issues we were running into. Then we're going to talk about the data parsing, then how we're creating the features and the vectorization. Then we're going to talk about the algorithms we used for this project, followed by the results we get. In the end of the video, we're going to talk about the future work we can do in this area and looking forward.
So the idea for a project was to use machine learning techniques to create summaries from texts. In order to do this, we used two datasets that comprise both of text and annotations or summaries of those texts. We used a supervised learning approach, which means we manually crafted the features for each sentence. In this project, we used both the NumPy and scikit Python libraries and then used an SVM to categorize the sentences. Basically, what we're trying to do here is determine whether a sentence is or isn't important towards a summary. And if it is, we choose it and we use it to summarize a text. Work has been done in both extractive and abstractive summarization. In this project, we focus on extractive summarization. Some problems with it is that the human effort to create datasets aimed at extractive text summarization is huge. And even when they're created, they inherently have the bias of whoever has summarized the data or the texts. And so consequently, there are very few datasets available for it. The first dataset we used was BC3, which is a corpus that was acquired from a research paper from the University of British Columbia and was initially intended for email summarization. The corpus consists of 40 email threads with a total of 3,222 sentences. Each thread has been annotated by 3 different annotators, and each email has a respective extractive summary. The second dataset we used was called Timeline 17. It was not initially meant for text summarization, but it's a much larger dataset. It was designed for timeline creation, and it contains 17 files that are composed of sub-files relating to different news channels. Each channel has its own timeline and several folders of data on news. These timelines were extractively constructed, so essentially they represent a summary of their respective article, so it could be adapted to serve the purpose of a project. Some issues we ran into were the size of the data. The total size of the articles amounted to 40 megabytes, and performing the calculations that we required on them took a lot of time. So we couldn't use all of the data we had. So to do this, we just took a chunk of the data and run our code with it. When trying to use larger amounts of data, our console would eventually error. For the data parsing, in the case of BC3, the main issue was dealing with limitators. This was also actually a problem with Timeline 17, I'll talk about later. But not every period determines the end of a sentence, so it was very hard to separate the text in sentences, harder than expected. Each email and each thread were observed as chunks of texts, and the annotated sentences were used as respective summaries. Then each sentence was labeled as either important if it appeared in the summary or not important if it did not. For Timeline 17, it was more complicated since it was not designed for this use. We use a recursive function to access all the files, and every file would then be dumped into a new file that would contain all the articles in it. Once this was done, the text had a lot of errors that would harm the results of our data. These are some of the issues we had to deal with when parsing this data. All these sentences or sentences that resemble these ones had to be deleted because they were articles relating to something else or links to other web pages, etc. Another issue was that not all the articles in the dataset were used to create an extractive timeline. So those articles had to be deleted to avoid over-punishing the algorithm. Afterwards, each sentence was labeled according to whether it had been used to summarize the article or not, and both datasets were merged together. Towards finding the features, we also had some trouble. since BC3 has metadata, but Timeline 17 has not, and metadata accounts for a large amount of the features that you find in text summarization literature for machine learning. So we didn't have access to this metadata since we couldn't find it across the board in our data, and we ended up not having enough, or what we considered to be enough relevant features in the data itself. Some of the features we considered were relative length, which punishes sentences for being too short, text similarity, centroid proximity, and TF-IDF, which my partner will talk about later, and sentence position, sentence to sentence, or centroid cohesion, etc. Each sentence was then converted into a vector of features. Now my partner will explain two of our more important features.
So TF-IDF is the short for term frequency inverse document frequency. It reflects how important a word is to a document in the corpus. So TF-IDF is calculated by the term frequency, which is a row count, times the IDF, which is calculated by log the number of documents over the number of documents with a term in it. So we first calculate the TF-IDF for each word, then we sum up the TF-IDF for each word in a sentence, then we take the normalize of the value. The centroid proximity is calculated by the following way. So first we sum up all the sentence vectors, then we normalize to get the centroid. In order to get the sentence vectors, we first generate a dictionary containing all the words in the text. Then the jth component of ith word is 1, which means that the jth word is in ith sentence. Otherwise, it's 0. So then we calculate the similarity to the centroid for each sentence. The method we use is cosine similarity. After get the features, we use SVM to categorize the data. First, we split into training set and a test set. Then we check the error rate. We used scikit and fed it into a SVM support vector machine using 3 different kernels.
After feeding our data into the SVM, we were able to calculate error rates. Across the board, we got extremely low error rates, around 3 to 4% on each run. However, we don't believe this was indicative of successful code, as these error rates were unrealistic compared to, say, 40% in a lot of the literature we found. We believe this problem points to a larger problem with the data, and that is that it's very biased towards penalizing the sentences for not being relevant. To fix this, some feature where that could be done is rebalancing the data. So what we think happened with the data was some of these summaries were very short compared to the articles where they came from. Thus, you end up with a very, very large amounts of sentences labeled not relevant, and very few sentences labeled relevant. To fix this, we could include a threshold for text to summary size ratio, which would eliminate the articles that are bigger compared to their extractive summaries. Additionally, we could use more of the data after rebalancing it in order to get better results, which we think would be possible. And ultimately, we think the most helpful thing would be to find more relevant features outside the ones that we used. For example, access to the title of the articles would be useful towards determining similarity between a sentence and the title, which is across most literature a very relevant feature for every sentence. Thank you very much for listening.
Thank you for watching.